Hello everyone, welcome back to the concepts of engineering mathematics course. So in the previous lecture, we saw how we can solve the simultaneous equations. Okay. And then we also saw a new method known as the row reduction method for solving the simultaneous equations. And after that, we started the discussion on vectors. So during that, we had seen what are vectors and how are they represented, and how the resolution can be done, what is meant by unit vector, and then we saw the addition and subtraction of vectors. So now let us discuss about the multiplication of vectors. So vector multiplication can be done in two different ways, and therefore the products are known as scalar and vector products respectively. Okay. And as the name suggests, scalar product will result into a scalar quantity, and the vector product will yield a vector quantity. So let us see them one by one. Okay. So we will now see the multiplication of vectors. Multiplication of vectors. Okay. So very firstly, the product of two vectors can be done in or gives the result in two different ways. The product of two vectors results in two different ways. So gives two different types of results. Two different types of results. So one is scalar type and the other can be obtained as a vector. Okay. Thus, the product is categorized as as dot product and cross product. So these names dot and cross are the standard ways to represent these two different type of products. So dot product is represented by a dot, and the cross product is represented using a cross. Okay. So as dot product. Okay. So this is represented like, suppose we have vector A and vector B. So the dot product will be vector A dot vector B, and the cross product will be cross product is written as vector A cross vector B. So in this way, the two type of products are represented. So let us see what is meant by scalar or dot product. So we'll now see the scalar or dot product. Okay. So the scalar product is defined as the magnitude of, suppose we have two vectors, vector A and vector B, then in this case, the dot product will be defined as magnitude of A multiplied by magnitude of B and multiplied by the cosine of angle between the two vectors. Okay. So the scalar product or dot product or dot product of say vector A and vector B, two vectors A and B is defined to be is defined as magnitude of vector A multiplied by magnitude of vector B multiplied by the cosine of angle between them. Uh, Let me use a different color. So this will be much more clear. So this is magnitude of vector A multiplied by magnitude of vector B multiplied by the cosine of angle between them. Okay. And it is a scalar quantity. It is a scalar quantity, which means it will only have the magnitude and will not have the direction. Scalar quantity. Okay. And here theta is the angle between vector A and vector B. Theta is angle between vector A and vector B. Okay. So symbolically, how it can be represented is symbolically this is written as vector A dot vector B is nothing but the magnitude of vector A multiplied by magnitude of vector B multiplied by cos theta. Okay. So this dot itself uh, between the two vectors gives the name dot product. And this type of product of vectors is commutative in nature. Okay. So the scalar product is commutative. Commutative. Okay. Okay, so let us see how this is obtained. Okay, so suppose we have two vectors, vector A, which is given as ax I cap plus ay j cap plus az k cap, and we have another vector B, which is given as bx I cap plus by j cap plus bz k cap. Okay. So if we want to take their dot product, then we simply multiply them. Vector A dot vector B is written as the first vector will be now multiplied with second vector. So this is nothing but axi plus ayj plus azk. Okay. And this is now dot multiplied with pxi plus byj plus bzk. So what happens here is we get say ax bx I dot I, because these are unit vectors, so these will again be multiplied as vectors. Okay, so I dot I, then we will have say ax by I dot j, then we will have ax bz I dot k, and then we'll have say ay bx j dot I. Here we will have ay by j dot j, then we will have ay bz j dot k, then we will have az bx k dot I, and then az by k dot j, then az bz k dot k. Now we know that this I, j, k represent the unit vectors along the coordinate axis, and the three coordinate axes are orthogonal, or means they are perpendicular, mutually perpendicular. Okay, so if we multiply the unit vectors, say, let us see. So suppose we have I dot I, then this will be nothing but the magnitude of I into magnitude of I into cos theta. Okay, so what will happen here is magnitude is 1, and this is again 1 multiplied by, this is not the cross of the cross product, so this is 1 multiplied 1, let me put dot only so there will be no confusion, and this is now multiplied with cos theta. So here the angle between two parallel vectors will be 0 degree. Okay, or means a vector is I cap, so it is in the x direction and magnitude as 1. Another vector is I cap, which is again in the x direction and unit vector magnitude is 1. So angle between them will be 0. So this is cos 0, and cos 0 degree is nothing but 1. So we will ultimately get this product as 1. But if any of the other unit vectors is brought here, suppose I dot j we do, then here what will happen is magnitude will be magnitude of I, magnitude of j. That is fine. But the angle here will be 90 degree. Okay, so this will be 1 into cos of 90 degree, because they are perpendicular, and cos 90 is 0, so this product comes out to be 0. Okay, so from here it is clear that the dot product of parallel vectors will be 1, means the angle between them is 0, so cos 0 will be 1. So actually I will rephrase my sentence that the dot product of two unit vectors which are parallel will be 1, like I dot I or j dot j or k dot k, and the dot product of two unit vectors which are perpendicular will be 0, because the angle between them will be 90 degree. Okay, so what it means that we will have I dot I as 1. Okay, sorry, I dot I will be equal to j dot j, this will be equal to k dot k, this will be equal to 1, and apart from this all others like I dot j will be equal to j dot I, and again this will be similar like I dot k or k dot I, or say j dot k or k dot j. All these will be 0, because these vectors are perpendicular to each other. Okay, so if we substitute these values in the dot product of a b, then what we get, therefore vector a dot vector b will be nothing but the terms where there are I dot I, j dot j and k dot k will remain, and others will vanish. Okay, so they will be left out with ax bx plus ay by plus az bz. Okay, so this is how the dot product is evaluated. So if we are given with two vectors, then to find the dot product we simply need to multiply the corresponding components, means x component multiplied with x component, y component multiplied with y, and z1 with z. Okay, so in this way the dot product can be obtained. So this becomes an important result. So suppose we are given with two different vectors uh, in the component form. So, say ax I cap plus b, ay j cap plus az k cap, and similarly for b. So if this form is given, then we can find the angle between these two vectors using the dot product. Okay, so how is it done? So uh, we know that the dot product can be written like this. Also, the dot product can be written like magnitude of vector A into magnitude of vector B into cos theta, where theta will be the angle between these two, will be equal to ax bx. Let me write that ax bx plus, sorry, this is ay by plus az bz. Okay, and if we bring this magnitude to the right hand side, then this becomes cos theta is ax bx plus ay by plus az bz over magnitude of vector A and magnitude of vector B. So if we are given with two vectors, we can find the angle between them. Okay. So now let us see the geometrical interpretation of this scalar product. So now the geometrical interpretation of scalar product. Geometrical interpretation of scalar product means, what does this signify geometrically? Yes, since we have seen that vectors can be represented geometrically and can be added, subtracted, or operated geometrically, so product will also be represented this using this way or in geometrical form. Okay, so this basically represents that it is the product of one vector and the length of projection of the other vector in the direction of first one. Okay. This will be clear with the help of schematics or means geometrical drawings. So let us say we have two vectors. Okay, so the first one is say vector OA and the other is vector OB. So suppose we have two vectors like this. Okay. So this is the vector say OA and say this is vector OB. Okay, means we can say that this is say vector A and this is vector B, and they have an angle of theta between them. Okay, so this is how these are there. Okay, so I said that the scalar product means it is the product of the first vector and the length of projection of the second on the first. So suppose our first vector is OA, then what I want to say is that the scalar product is nothing but the product of length, means multiplication of the length of the first. Okay, so this will be, this is nothing but vector A dot vector B is nothing but the distance OA, the length of the first vector multiplied by the length of projection of the second vector is OB. So length of projection of vector OB on the first vector, and geometrically this will be nothing but this length will be the projection here. Okay, so this is the projected length which will be say OC. Okay, so this is nothing but multiplied by OC, and OC will be nothing but OB cos theta. Okay, so this will be OA into OB into cos theta. Okay. And we know that if we want to write it down, so this can be written as nothing but OA is the magnitude of vector A. We know that magnitude gives us the length. So vector A, and OB again is the magnitude of vector B, and this is cos theta. So we have now again arrived at the same result that we saw earlier. This is how it is signified geometrically. Okay. So this dot product is nothing but length of vector A, length of vector A. Okay, it is multiplied by the projection of vector B along vector A. This is now multiplied with projection of vector B along vector A. Okay. So in this way, the geometrical significance is um, shown here. Okay. So let me write it also that the scalar product of two vectors is the product of one vector is the product of one vector and the length of projection and the length of projection. This was product of length of one vector. Okay. So two vectors is the product of length of one vector and the length of projection of the other in the direction of the first one. In the direction of the first. So this gives us the geometrical interpretation of scalar product of vectors. Okay. And this scalar product finds its application in various problems related to engineering concepts, as we have mentioned. Okay, so one of the examples of this application of this dot product is in work done. Okay, so work done is basically represented as the scalar dot product or dot product of the force vector and the displacement vector. Okay, so suppose a constant force acts on a particle and the particles gets displaced by some vector, say d or vector b or anything. So the dot product of the force vector and the displacement vector will give us the amount of work done in displacing that particle. Okay. So we have application of dot product as work done. Work done. Okay. So suppose if a constant force x, so if a constant force F acting on a particle, acting on a particle displaces it, say from a point or position A to a new position B. Okay. Displaces it from A to B. Then the displacement vector is given as vector AB. Means this is the way of finding the displacement or position vectors. So if suppose a particle was initially at A and now displaces or moves to position B, then if we take the difference of coordinates of B and A, means coordinates of B minus the coordinates of A, and form a vector by that, then that vector will be the displacement vector. Okay. Displaces it from A to B. Then the work done in displacing is given as, then work done in displacing the particle, say W, is given as the force multiplied by displacement, the force dot displacement. Okay. So this is an important relationship used for various engineering problems related to work. Okay. So with this we have now seen important things related to the scalar product or dot product of vectors. So let us quickly solve an example or numerical to find the angle between two vectors if the vectors are given, and then we will see the vector product or cross product. Okay. So suppose we are given with two vectors. Okay, so we have to find the angle between say vector A is nothing but I cap plus j cap. Okay, and vector B is given as I cap plus j cap plus k cap. Okay, so in order to find the angle, what we need to do, we know that the angle is given as the dot product of the vectors divided by their respective magnitudes. Okay. So cosine of angle between them is nothing but the vector A dot vector B. This is the dot product, and this will be divided by magnitude of vector A and magnitude of vector B. Okay. So let us see what is the dot product. Okay. So now vector A dot vector B is nothing but, we have seen that the respective components get multiplied, means AX will be multiplied to BX, AY to BY, and AZ to BZ. Okay. So here AX is nothing but 1 and BX is also 1. So A dot B will be 1. Then we will add the product of next components. So 1 into 1 again 1, and the Z component of vector A is 0 here. Okay. So 0 into 1 will result in 0. So this comes out to be 2. Okay. So here it also becomes clear that the dot product results in a scalar value. Okay. So 2 is a scalar. Now we will need the magnitudes of vector A and vector B also. Okay. So sorry. So magnitude of vector A is nothing but the square root of squares sum of squares of all the components. So this will be 1 square plus 1 square plus 0 square, which is nothing but root of 2, and the magnitude of vector B will be nothing but under root of 1 square plus 1 square plus 1 square. Okay. This will be root 3. So from these values we can write cos theta will be nothing but 2 by root 2 into root 3. So this root 2 gets cancelled out from the numerator. So this will be root 2 by root 3. And you can solve this using the standard scientific calculators. So this theta value comes out to be cos inverse of root 2 by root of 2 by 3. This can be written as root of 2 by 3. And upon solving, this value comes out to be approximately 35.26 degrees. So in this way, we can find the angle between two vectors if the vectors are given to us. Okay. And this method of finding the angles also gives us an important result, which we had seen also, that the dot product of any two perpendicular vectors will be 0, okay, because the angle between them will be 90 degree and cos 90 is 0. So let us write this as a point also, as an important point. So the dot product of two perpendicular vectors is 0. Okay. So this is an important result. So with this, let us now see about the vector product. Okay. So we are over with scalar product. Let us begin the vector or dot cross product. Okay, so let us begin the vector or cross product. And we have seen that this is represented using a cross. Okay, so vector product or cross product. Cross product. So this type of product results in a vector quantity. So suppose a vector A is cross multiplied with vector B, then the result will be a vector quantity, and that particular vector quantity will be perpendicular to both of these vectors. Okay, so the vector product, the vector or cross product or cross product of two vectors say vector A and B is defined as a vector such that the magnitude is, since this is the result is a vector, it will have magnitude as well as direction. So we should define the conditions to determine the magnitude and to find the direction. Okay, so such that its magnitude is given as that its magnitude is magnitude of vector A into magnitude of vector B into the sine of angle between them. Okay, where theta is the angle between vector A and B. Okay, where theta is the angle between vector A and vector B. Okay, so this gives us the magnitude, and the direction of this vector or the product one should be perpendicular to both the vectors A and B. Okay. So its direction is perpendicular to both vector A and vector B. Okay. And the method to determine the direction is through right hand thumb rule or right hand screw rule. Okay, so you would have seen that suppose if we have the first vector, say this is my right hand. Okay, so it's suppose we have a vector in this direction and another is in like this direction. Okay, so like this we have two vectors. So now to find the cross product direction, what we need to do is curl our right hand from the from the direction of first vector to the direction of second vector, and the direction in which our thumb will point will give us the direction of cross product vector. Okay, so say this was vector A and this was vector B, then I need to put my right hand in the direction of vector A if I am trying to find A cross B. So A and then cross B. So A cross B, like this I will do. So my thumb, this is pointing towards me. So this gives us the direction of cross product. Okay. So this is the right hand thumb rule. Similarly, there is the right hand screw rule. So if we place the tip of a right-handed screw at the joining point of the two vectors and curl it from first vector to the second one, it will give us the direction. So suppose this was vector A, like this vector A, and this is vector B, and we have to find the cross of these two. So vector A cross B. So I'll put a right-handed screw here and I'll rotate it. So right-handed screw goes like this. Okay, so it proceeds forward when moving clockwise. So this will give us the direction of movement of a screw will give the direction of cross product. Okay. So these are two methods. So the direction is found using right-handed system. RIGHT, right hand thumb rule or the right-handed screw rule. Right-handed screw rule. So these are the techniques which are used to determine the direction of cross product of two vectors. Okay. And suppose now we need to write this entire thing in the form of a mathematical expression. Then we will need the magnitude, which we see can be written as A, B sine theta. We also need the direction. So suppose eta cap represents, or say n cap represents the direction which is normal to both vectors A and vector B. Then in that case, say let eta cap represents, or say n cap. Okay. So say n cap be a unit vector. Since we only need the direction, that's why we will take a unit vector. So be a unit vector perpendicular to both vector A and vector B. Okay. Then the cross product can be mathematically written as vector A cross vector B is equal to magnitude of vector A, magnitude of vector B into sine theta into n cap. Okay. So now we have everything. We have the magnitude, we have the direction. Okay. So in this way, the cross product is represented. So let us see the geometrical interpretation also. How is it happening geometrically? So as I mentioned, suppose we have two vectors, vector A and vector B. So like this, say we have vector A and we have another vector, say vector B here. Okay, so in order to find the cross product, we can find the magnitude by multiplying their respective magnitudes and multiplying them with the angle between them. And to find the angle, we need to place them tail to tail. It means tail of first vector will be placed with over the tail of another one. Okay, so say this was our vector A and this is vector B. We have placed them tail to tail. Then this angle is theta. Okay, so magnitude is given by magnitude of A, magnitude of B into sine theta. And now to find the direction, if we are doing A cross B, then we need to move from A to B using the right hand thumb rule. Okay, so here say this is A and this is B. So like this, A cross B. Okay, so this is representing that the direction is, it might be appearing to you like it is coming out of the screen, but this is going into the screen. Okay, say like this for you, say this is this will be like right hand. Okay, so as I mentioned, it should be away from you. So say this is A cross B, so this is coming away. Okay, I use the left hand just to demonstrate. Actually we should use right hand. Okay. So suppose this was vector A and now we are moving in a sense like this. So this is the moving sense clockwise using the right hand. So this ultimately results in downward arrow. Okay. So means say this is going into the plane of this paper or sheet. Okay. So this goes in like this. So the direction of cross product will be into the sheet of this plain paper or this screen. Okay. So magnitude can be written as E. Since we are writing the magnitude, this is represented or denoted as, we have taken the capital alphabets. So vector A cross vector B will be nothing but magnitude of A, magnitude of vector A, magnitude of vector B into sine theta. Okay. And direction we have seen, how can we find it? Okay. And this only makes it clear that this cross product is anti-commutative. Okay, means this is not commutative, this is anti-commutative. Let us see how that happens. So if we take the same two vectors and we now try to find B cross A, then in that case we will move our hand from B to A. Okay, so here we had A to B. We were moving from A to B. Now we will move from, I'm shifting the vectors because as I mentioned earlier, we can shift the vector parallelly. Okay, without changing its magnitude, it will remain same. So we are now moving from B to vector A. Okay. So we are now moving like this. Okay. This is vector B and this is vector A. We are moving from B to A. So if we move our right hand like this, curl our fingers of the right hand like this, so thumb will point out of this screen or out from the plane of paper. Okay. So like this is represented by this. This is coming out. Okay. So our thumb is coming out. So this represents, this was for A cross B. A cross B, and this is for B cross A. Okay. And magnitude will remain unchanged because it will again be magnitude of B multiplied by magnitude of A multiplied by sine theta, and angle is not going to change here. So B cross A will have the same magnitude. Okay. It can be written as magnitude of A, magnitude of B into sine theta. So magnitude is not going to change. Okay. This is like this. Okay. Magnitude is unchanged, but direction gets reversed, and when we reverse the direction of vector, it is followed by a negative sign. So what does this mean? It means that b cross a is nothing but negative of a cross b, because the magnitude was same, only the direction got reversed. So this is the result, which indicates that vector product is not commutative. Vector product is not commutative. Okay. So now let us try to find the cross product using two vectors like we did for scalar product, and this result will now indicate that this cross product can be represented, or vector product can be represented in the form of a determinant. Okay, so that will make the finding of vector product much easier. So now let us say we again have two vectors, vector a, which is ax I cap plus b ay j cap plus az k cap. Okay. And we have another vector b, which is given as bx I cap plus by j cap plus bz k cap. Okay. Now if we multiply them, since we are doing the vector product, we will write it as a cross b. So a cross b is again this ax I plus ay j plus az k is being cross multiplied with bx I plus by j plus bz k. Okay. And if we expand this multiplication, what we get is vector a cross b is nothing but, since I, j, k are unit vectors, so they will be vectorially multiplied. Means they will follow the product type which is being used here. Cross product is there. Okay, so this is ax bx I cap cross I cap plus ax by I cross j I cap cross j cap plus ax bz I cap cross k cap. Okay. And similarly this will be now ay bx j cross I plus ay by j cross j. Okay. Then we have now ay bz, and this is j cross k. Okay. Now we will have az bx k cross I plus this is az by k cross j, and then we have az bz k cross k. Okay. So using this, now we can find the, or we can simplify these terms. So for that we need to know what will be the values of these I cross I or j cross k, or means what they mutually mean. So if we try to find, now say we try to find I cap cross I cap, then we know that this is given as modulus magnitude of I magnitude of I, sine theta. Again, see, these are two parallel unit vectors. So magnitude will be 1 and 1, and angle between them is going to be 0 degree since they are parallel. And here sine 0 is 0. Okay. In the case of dot, it was cos 0, so it was coming 1, but here sine 0 is 0. So sine theta and say n cap. So here 1 into 0 into anything will be 0 only. Okay. So this gives us 0. In fact, 0 vector is also a null vector, but we'll not going into that detail. So this is 0. So I cross I is 0. Similarly, we will have j cross j and k cross k will also be 0 due to angle between them is 0 due to this reason. Okay, so j cross j and k cross k are all equal to I cross I, which is equal to 0. Okay. Now, what happens for this I cross j? Okay. So I cross j will again be magnitude of I, magnitude of j, and this will be sine theta and cap. Now magnitude is 1 for I, magnitude is 1 for j, and we know that these two vectors are mutually perpendicular. Okay, since these represents the direction along axis, so which are orthogonal. Okay, so sine theta will be sine 90, which is 1. Okay, so 1 into 1 into 1. Now what about the direction? So we know that the direction of the cross product should be such that the vector which is formed after cross product is perpendicular to both the vectors of which it is the product. So for I and j, k is the vector which is perpendicular to both of them. Okay. So see here, the positive z-axis and negative z-axis, both cases are possible for being perpendicular to these two. But as a convention, we will take the positive for positive value, okay, or we will follow a order. Okay, so this will be 1 into 1 into 1 into k cap. Okay, k cap is perpendicular to both of these. Okay, so that's why I cross j will be nothing but k cap. Okay, and for the convention we will follow like okay. Either we can follow the cyclic clockwise or anti-clockwise system. So let us say we are now following this anti-clockwise. Okay, so like this. So if we have I, we have j, then we will have k cap here. Okay, means I cross j will result in k, j cross k will result in I, and k cross I will result in j. And if any of the order is changed, automatically the sign will get changed to indicate the reversing of vector. Okay, and this again is a unit vector. Okay, so therefore I cross j is k. Similarly, I have mentioned that j cross k will now be I, and this k cross I will be j cap, and if it is reversed, j cross I we find, then it will be minus k cap. Okay, similarly, k cross j will be minus I cap. Okay. This was minus k cap, this is minus I cap, and if you try to find I cross k, then in that case it will be minus j cap. Okay. So using these results, now let us find what is the value of this a cross b. So due to this, the product a cross b now becomes, this was I cross I, so this is 0. So we have now ax by, and I cross j is k, so this is k cap. Then we have ax bz, and we have now I cross k, which is minus j, so this changes to minus sign, minus j cap. Similarly, j cross I is minus k, so minus of a y dx. Then we have j cross j, which will be 0. Then j cross k is plus I, so plus of a y dz. This was j cross I, so k minus we have considered. Okay, and this is j cross k is I. Okay. Similarly, here again we will have az bx. Okay, so this is az bx, and k cross I. K cross I is j. Okay, so plus of az bx j cap, then plus k cross j will be minus I, so this is negative of az by k cross j is minus I, so minus we have considered, so I. Okay, now let us rearrange them. Okay, so how they appear now? This becomes a cross b is nothing but, let us club the items together, so this becomes ay bz minus az by I cap. Then we have the j terms, so plus, let me take the minus outside, so this is ax bz minus az bx j cap, and then we have the term which is ax by minus ay bx j cap. Okay. So now if we observe it carefully, this is nothing but the determinant formed by I, j, k and ax, ay, az and bx, by, bz. Okay. So we will now revert it back to the determinant form. Okay. So say we while expanding the determinants, we considered one of the rows and then found its cofactors and multiplied with them and then added them together. So now we will do the reverse. Okay. So while reversing, what we get is, say this was the initial row which we took. Okay, and if you will observe closely, then these factors will form the cofactors like this. Okay, so this is bx, by and bz. Okay. So if we take for suppose I cap, then I cap is kept like it is, and here the cofactor power we will have minus 1 to power 1 plus 1. So minus 1 to power 1 plus 1 will be 1 only. So positive sign, and this then this ay bz minus az by. Okay. So in this way, the cross product can be represented as a determinant. Okay. So this gives us the way to find the cross product. Okay. And also like there was an important result for dot product, that the dot product of perpendicular vectors is 0. Here the cross product of parallel vectors will be 0 because the angle between them will be 0 degree and sine 0 is 0. Okay. So the cross product of parallel vectors is 0. And this concept can be used to find the coplanarity of any given two vectors. Okay, so suppose if two vectors are given, and suppose three vectors are given, and we need to find that whether two of them are coplanar or not. So for them to be coplanar, they both should be perpendicular to the third one. Okay. So that is the concept of this vector product. Okay, so with this we have now come to the conclusion of this multiplication of vectors also. Okay, so uh, let us now close this session. So we have now learned the concepts like determinants and matrices and vectors, and also have seen their application in solving various problems related to day-to-day life, related to various engineering concepts. So this was the application of mathematics in engineering applications or problems. So thank you very much.